Hello and welcome to the Ecological Design Modeling series. This is lesson 5C, simulating the fish model in Excel spreadsheet. So we see here we have the various components of the model. So let's review what those are. Again, this is the fish model, and over here we have the diagram of the fish. We have a storage representing the quantity of fish in mass. We have an inflow coming from a source. We have an outflow, or our e-migration, of fish leaving the system. And then we have a fishing effort with our interaction symbol that's removing fish. So this is our take, and then this would be the production of fish, or the fish that we actually catch or land. The various components are the equation dq over dt equals k1e minus k2q minus k3qf. We should see how that comes directly from the diagram on the right hand side here. K1e is an inflow, it's positive. K2q is an outflow, therefore it's a negative in the equation. K3qf is also an outflow and is a negative in the equation as well. And note that we have three pathways, one input, two outputs, so we have three terms in our change equation. We have one storage, therefore we have one differential equation. Step 2 is we have the calibration values here. If you recall back to the lessons from the whiteboard, we have an inflow, K1E, or J1, equals 5 grams per square meter. That's this 5 here in the diagram. J2 is our e-migration, that's 3 grams. We see that on the diagram as well. J3 is our take of fish, and that's 2 grams, and that's this 2 here. We also have a source of fish, which is 10 metric tons, and we have our storage, Q, the tank. We also have fish, in this case it's 10 labor hours per day. On the whiteboard example, we were calling this 10 boats. For our purposes, we can go either way. We'll stick with labor hours since that's what is in the spreadsheet. So from these calibration values, again, these would be values that we would use either sampling methods to go out to our fishery and measure what these flows are, what the storages are, or maybe we would go to literature and develop best estimates of what these flows and storages would be. And then to calibrate our model, or to estimate what the pathway coefficients equal, we solve each of our individual terms or pathways. Similarly, if I click on the formula bar for what K2 equals, it's what's in H6 over H9, or J2 over Q. Finally, we have K3 equals J3 over Q over F. And we see that value is 0.0002 over labor hours, days. And that also refers back to our calibration values here. So what's important to remember is that the calibration is conducted before the simulation. We determine what the K values are, and these are set. They're constants, meaning they're constant throughout the simulation, and they do not change. Our next step is to develop initial values for the variables, the sources, that are part of the simulation. So in this case, we have two sources, E and F, so they need initial values. And in this case, they're going to be constant throughout the simulation. Later on, we will explore how E and F, or sources, don't have to be constants. But for now, the simplest assumption is to assume that they are constant. We always need an initial value for our storages. In this case, we have one storage Q, and its initial value in this case is 224 grams. Finally, we need to determine what we want our time step to be, or dt. In this case, we're going to use 1 day. Our units are, the flow rates are in per day units, so using a time step of a day seems plausible at this point. Step 4, we have the simulation itself. So the components of the simulation are the time during our simulation. In this case it's days, so that's a column. And then each of our sources, flows, and storages, as well as our change equation, are columns within the model. Our source E is a column. Again, it's constant, so it's going to be 12 throughout. Our fishing effort, labor hours, although it's mislabeled here as boats, is also constant, 8 labor hours. Next, we have the inflow, K1E, or our new supply of fish, which is a calculation. We'll go over that in a second. And then we have our natural loss, K2Q, or our E-migration. And then we have our take, what's actually being harvested as we fish, K3QF. And finally, we sum all of our flows together as our DQ, or change in storage. So again, the simulation is referring back to our calibration coefficients as well as our initial values up above. So our source, here we said it's 12, so once we've entered 12 into the B7 cell, we can just refer to that with our dollar signs and copy that down so that every row of the simulation refers back to this B7 cell. And if we scroll down, we can see that the formula bar value B7 stays the same with the dollar signs. The fishing effort also is constant throughout the simulation, but in this case we did the formula slightly different. Instead of using the dollar signs, we refer to B8 in the cell here, but then our next cell just refers to the previous cell, dollar signs, and then that can be copied down. As long as we're always using the values here, and if we change these values, it changes the column. So for example, instead of making F8, if I made it 4, I should see 4 change throughout my column here. Our initial value for Q, our fish mass or stock, is 224. That refers to the B10 cell. Next we'll go to day 1. So on day 1 we have a flow of new fish coming in, and it's K1E. It's always K1E. What is that? It refers back to K1 up here in our calibration area, 5. Note that has dollar signs. And then it refers to our B14 over on the left-hand side in our second column. That equation is just copied down. Note that it's always multiplying times the value of E at the previous time. Our natural loss of fish is K2Q, and our equation again refers back to K2 from our calibration area in the orange into our previous value of Q. Whereas K1E is 2 constants multiplied together, so it's always a constant 6 in this case. Q is not constant, but K2 is. Therefore, K2Q is not constant. Our fish take, K3QF, is using the K3 coefficient and multiplying times the F and the Q from the previous time step. Next, DQ is the sum of the inflows and outflows, so it's plus K1E minus K2Q minus K3QF, or we can see by highlighting the formula bar the cells that it's referring to. Also importantly, it's referring to the time step, so the whole change is multiplied times dt, and this is what dq equals. Therefore, if we change the time step, will change DQ. A smaller time step means that DQ will be smaller as well. And finally, in the simulation, we want Q, our new value at time 1, to be the old value, or the value at time 0, plus the change that occurred during the first day. So you can see here by highlighting the formula bar, it's the D14 cell plus the H15 cell.